Hello everybody, my name is Yu-Kuan Hsiao. I am a graduate student currently studied at National Chung-Hsing University in Department of Electrical Engineering. Today I'm going to present about reconfigurable hardware architecture design and implementation for AI deep learning accelerator. First of all, I will give a brief introduction and what SRAM size we choose to get the best efficient bandwidth according to analyze, and how we practice in hardware for getting better utilization. In neural network, we implement on is tiny YOLO V2. The input is 416 by 416, and the three-dimensional output is obtained through multiple convolution operations and max pooling operations. And so the post-processing method, the frame and the object type are marked. The operation of this architecture includes convolution stride is 1, kernel size is 3 by 3 or 1 by 1, max pooling max is 2 by 2, and stride is 1 or 2. In order to design a CNN hardware accelerator suitable for tiny YOLO V2, we first analyze the data volume of each layer, and we can find that the size of the input decreases as the number of layers increase, and the weight is opposite. For getting the best efficient bandwidth, the SRAM size of input feature maps and kernel is critical. After the analysis, the best trade-off of SRAM size of weight is 144 kilobyte, and the bandwidth is 1.98 gigabyte. Here's the evaluation of tiny YOLO V2 for each layer. The market value are the total data size of all layers. In normal way, output feature will transmit to DRAM after operating of each layer. The total bandwidth will be 2.69 gigabytes per second. Our design provides a method to do max pooling directly after convolution before transmit to DRAM. According to our method, we can decrease all transmitting concentration of max pooling layer. Then the bandwidth can decrease to 1.98 gigabytes per second. And this is the overall architecture. DRAM is the place where the in-output feature, bias, and weight are placed. Input feature map, weights, and bias will be transmitted to global buffer, which contain 9 SRAM for different categories. And the value in global buffer will be transmitted to PE through the system control unit for calculation, and written back to global buffer. According to layer process, if next layer is convolution layer, else if next layer is max pooling layer, will have different transmission. I will present detailed process later. Here's the construction of our global buffer design. It constructed by 9 SRAM, respectively are bias buffer, weight buffer, 3 input feature map buffer, which are for 3 rows of input, 2 convolution buffers, which are for the result of convolution operation, and the output feature map buffer, which is for the result of max pooling operation. The detailed transmission of our data can separate in 2 parts. One is next layer is convolution, and the other is next layer is max pooling. No matter which condition, first we make bias, weight, and input features transmit to each SRAM in global buffer from DRAM. If the next layer is convolution, bias, weight, and input feature will transmit to processing engine to do convolution and get a result which is the rate level on this page. then store the value in convolution buffer, which can also be called SRAM3. Until all three rows down, the value can be stored in SRAM3 can directly transmit to DRAM continuously. The next row of data will replace SRAM0 in order to decrease the transmission times by reusing SRAM1 and SRAM2 data. Respectively, next will SRAM1 being replaced, then SRAM2 being replaced. If the next layer is max pooling, same as next layer is convolution. Bias, weight, and input features transmit to each SRAM in global buffer from DRAM. Bias, weight, and input feature will transmit to processing engine to do convolution. And get a result also is the red label on this page. Then store the value in SRAM3. And read next row of input feature from DRAM and replace SRAM0. Do the same operation, but this time the convolution result will store into SRAM4. Now we have two rows of convolution results that can meet the condition of doing max pooling operation. Max pooling result, which is the green label on this page, will store in SRAM5. After two rows of convolution buffer value down, the value of SRAM5 transmit to DRAM. Here's our processing engine architecture. Input feature map, weights, and bias come from global buffer. Our PE array is constructed by 72 PEs, which compute per one cycle of 72 PEs. Will store into partial sum buffer until all three rows operation down. If the next layer is convolution mode, the partial sum will add bias, then do reloop before sending out to global buffer and send to SRAM. Else, if next layer is max pooling, the result of three rows operation will send to first convolution buffer directly, and so on. The next result sent to the second convolution buffer. Each column of PE array processes a 3x3 convolution. After the PE operation, the partial sum will be stored in the PS register. After a kernel is calculated, PS0 to PS7 are the result of the convolution operation. PS8 and PS9 are partial sum. The next operation will be putting the results of PS8 and PS9 into PS0 and PS1, while PS2 and PS9 will reset to 0. Since the characteristic of reloop will cause the feature map after the first layer of deep learning network to have many zeros, we have configured clock gate inside the PE so that the multiplier and deep flip-flop can directly output 0 without any action to reduce power. The synthesis result is by using TSMC 90nm process. Clock rate is 100 MHz. Total SRAM we use is 322 KB, and gate count is 140,000. Throughput is 14.4 GOPS. The lattice is comparison with other designs. In order to make all designs be compared fairly, here we use technology scaling to convert various processes to the same 90nm process as the paper. It can be seen that architecture proposed in our design is less used in gate count than other. Also, the 14.4 GOPS seems to be lower than other papers. It is because we can only have a 72 PE design based on the elimination of our current platform. In the future, our research will be based on this architecture and expand the design to 288 PEs. The data is as described in this table. Then GOPS will be able to surpass the throughput of other papers. And here's our reference.